Hi class. I want to talk about now a little bit more of Chapter 4 about gravity. Talk a little bit about Newton's law of gravity. We've already talked about Newton's laws of motion. We've mentioned law of gravity, but we haven't said too much about what the law of gravity allows you to calculate or to kind of visualize and understand in nature. So in this section, we're going to talk about the strength of gravity, what determines how strong gravity is, and how does Newton's law of gravity relate to Kepler's laws. So we've talked about Kepler's laws before, these three laws of planetary motion, which were laws that Kepler observed basically of the planets. Tycho had made these observations of the planets, the five bright planets that you could see with your naked eye, and he had really good data on their motion through the sky over the years. And Kepler was able to show that the motion of the planets obeyed certain laws, like elliptical orbits, and that the period of the orbit is related to the average distance from the planet to the star in some special way. So we're going to look at where those laws now come from. Newton's law of gravity allows us to determine where those laws of Kepler actually come from. So again, Kepler's laws were just observational. He just noticed that this is what was true. But why are those laws true? That comes from Newton's law of gravity. So Newton's law of gravity basically says that every mass attracts every other mass. So that's what gravity is. It's an attraction between masses. So if you have two masses, m1 and m2, and if they're a distance d apart from their centers, so d is measured from the centers of the two masses, then you can calculate a force of gravity by multiplying the two masses together, dividing by the square of the distance, times a constant, big G. Big G is just a number. It's a universal constant of gravity. And people have done experiments to really precisely measure this number. But it's a constant. It doesn't change. And so that, multiplying all these things together, gives you the force of gravity, the attractive force of gravity. And these two blue arrows show that this blue arrow that's kind of attached to M2 shows that it is being pulled toward M1. There's an attractive force on M2 coming from M1. But at the same time, because of Newton's third law, that action-reaction law that we had talked about, there is an equal but opposite force pulling on the other mass, M1, toward mass M2. So these two arrows are two different forces on two different masses, but they're equal and opposite to each other by Newton's third law. They're both gravitational forces. Their magnitude would be given by this equation. So this gravity equation applies to things that are balls. Okay, if you have a spherical shape and you're going to measure the distance between the centers, it applies to that. It applies to objects that are not balls, as long as their sizes are very small compared to their distances. But if you start to get objects that are kind of big and weird shaped, and their distances apart are not that big, then technically you have to do things a little bit more in a little bit more complicated way to calculate the force. But this equation still gives you a good approximation to the force. So for example, if you were standing next to somebody about a meter away from them, your size and the distance of a meter are kind of comparable. They're fairly similar. And so this equation wouldn't quite work unless you were a ball. If you kind of tucked yourself up into a ball, then maybe this equation would be more valid. But so you'd have to really do something a little bit more carefully using calculus, actually. So we're not going to do that. But you could approximate the force. So if you said you're standing next to somebody that has a mass of, let's say, 75 kilograms, and you have a mass of 100 kilograms, you'd multiply those two numbers together, so 75 times 100, and then you divide it by the distance between you, squared, in meters. So you divide by, let's say, 1 meter squared. So it'd be 75 times 100 divided by 1 squared. And then you'd multiply by g. Now g is a really small number. G is like 10 to the minus 11. 6 times 10 to the minus 11 is the number. So this number here is 75 times 100. So that'd be 7500, 7,500, divided by 1 squared, which is just 7500, and then times g, 10 to the minus 11. Okay, so the 7500 is 7.5 times 10 to the 3. Multiply that by 10 to the minus 11, you're going to get something like 10 to the minus 8. So 10 to the minus 8, and you know the numbers, we're not calculating this exactly, but 10 to the minus 8, and the force would be in newtons. The what we use to label forces is the unit called the newton. 10 to the minus 8 newtons. If you compare that to your weight is closer to, if you're 1,000 kilograms, your weight is closer to, or if your weight is 100, if your mass is 100 kilograms, your weight is closer to like 1,000 newtons. So 1,000 newtons is roughly approximately your weight. Compare that to about 10 to the minus 8 newtons for the force between you and the person standing next to you. The gravitational force is very weak. And so we don't feel it very well. We don't feel it between people standing next to each other or an object sitting on your desk. It experiences more of the gravitational force pulling it down toward the Earth than it does any other gravitational force, because all the others are so weak. But this is how you would calculate the gravitational force between two masses. So when you do that, if you think about the kinds of motion you could then have, if you think about a planet orbiting a star, what we find is that the star will be at one foci of the elliptical orbit, if we think about an elliptical orbit like we talked about earlier, and the planet would go around in an elliptical orbit possibly. Well, that's not the only option. That's not the only possibility. There are two other possibilities that lead to orbits that are not bound, that are not complete, that are not completely closed. They don't, the particle, the object doesn't come back again. And those are parabolic orbits and hyperbolic orbits. They have slightly different shapes to them, but they're both orbits where an object could come along, get attracted to the star, for example, get really close, but then swing out and get further and further away and never return again. And then the same thing for the hyperbolic orbit. It comes in at kind of a not as steep of an angle, sort of, not as squished as an orbit in a sense. It comes in, it still gets really close, but then it goes off away forever. So the parabolic orbit, that's just a particular mathematical shape, the parabola. And the hyperbola, the hyperbolic orbit, is again a particular mathematical shape. Those particular mathematical shapes are shapes of orbits that you can have that are sort of kind of created by or governed by the law of gravity. So for planets going around stars, we're always going to see the elliptical orbit. Otherwise, it's not very interesting. If the planet has a parabolic orbit, it just comes along and passes by the star once and then it's gone forever. It's not very interesting. So any planetary system that is bound, where the planets are going round and round and round, all the orbits are going to be ellipses. Sometimes the ellipse is actually almost like a circle. A circle is actually a special case of an ellipse. Right? And that would be where the sun is exactly at the center, and the planet is always the same distance away from the sun. Usually, though, the planet sometimes is a little bit further away, sometimes it's a little bit closer. And you can prove mathematically that law of gravity that we just looked at gives these three different types of mathematical shapes for the orbits of objects around other objects. So the ellipse is the only bound orbit. The parabolic and the hyperbolic orbits are unbound orbits. This is the Earth, and we're going to fire this cannonball up off this mountaintop. And we talked about how as soon as the cannonball is released, it's in free fall. It's simply going to fall because of the force of gravity. So as long as the only force acting on you is the force of gravity, then the orbits that you have are ellipses or parabolas or hyperbolas. Those are the shapes of the orbits. So if I fire this thing, first I have to make sure it orbits. So I fire it, I set the velocity at a certain speed, I fire the cannon. So it orbits. This shape is actually a parabola. It is a parabola. But it's not an orbit yet because it crashes. So I have to fire this a little bit faster. So fire it a little bit faster, reload the cannon, fire it, and I orbit a little bit further, but I still crash. All right. So there is a sort of a minimum velocity that I have to attain in order to get an orbit. So try that. 8 kilometers per second. Perfect. All right. So that 8 kilometers per second is the sort of the minimum velocity needed to get an orbit, and that orbit will actually be a circular orbit. A nice circular orbit, always the same distance from the center of the Earth. Okay, so a nice circular orbit, it's a bound orbit, allowed for by the law of gravity. Now, if I reload this and just increase the speed a little bit more to say 9, let's go to 10. Yeah, we'll stay at 9. All right, and now fire it. I have an orbit, but it's no longer a circular orbit, it's an elliptical orbit. But it's still an orbit. It's still a closed, bound orbit. So the object gets closer to the planet, and then it gets further away. So notice we talked about planets going around stars as one application of the law of gravity, but we can also talk about objects going around planets. In fact, we could talk about anything going around anything else. that is, if the force between them is the force of gravity, then we can talk about these orbits being ellipses, hyperbolas, or parabolas. So that's a little animation of things going around the Earth. Now there's another one which is kind of neat, and I talked about this before. If you Google PHET interactive simulations, again, these are by University of Colorado in Boulder. This is one that doesn't use Java, it uses HTML5, so it should run right in your browser window. So if we click on this, it brings up this little window here, gravity and orbits. And so we can go to the model module here, click on model, and it gives you the sun and it gives you a planet, the Earth over here. And you can zoom in and zoom out on this, or you can make it go fast or slow and so on. If you play it, it's going to show you what happens as the Earth goes around the sun. So we can turn on a couple things. Let's turn on the gravitational force. So this turns on an arrow showing that there's a gravitational force on the Earth toward the sun. That's what's going to keep the Earth going around the sun. But there's also a gravitational force on the sun toward the Earth. These are Newton's third law action-reaction partners. So while the Earth is getting pulled toward the sun is getting pulled toward the Earth. And so, but the sun is so much more massive than the Earth. And so when the Earth is orbiting, technically the sun is actually orbiting as well. But it's such a tiny orbit, and we'll talk about this in a second, it's such a tiny orbit that we hardly notice it at all. And for all practical purposes, at least for what we care about, you and I, we can just say the sun is sitting still. But this is in fact a way that they detect planets around other stars, is they look at stars wobbling. They can look at, by looking at the light coming from a star, and we'll talk about this in coming chapters, they'll look at the light coming from a star and they'll see from that light the fact that the star is actually moving back and forth. It's kind of wobbling back and forth. And that wobbling back and forth can be explained by an object orbiting that star. As the object orbits that star, the star gets pulled in different directions, and it literally wobbles. It literally orbits also. So not only is the planet orbiting, but the star is orbiting too. But for small planets like the Earth, the orbit of the star is negligible. It's very small. So let's just let that go. Let's let the Earth orbit. So there it orbits. So let's turn on its path so we can see the orbital path. So there's the orbital path of the Earth going around the sun. And then you can change some stuff. You can change the planet's mass, make it more massive, and see what happens. So it increases the gravitational pull, gives you a bigger force, increase the sun's mass, the force gets bigger, right? And you can do different things and change its, so notice how the orbit is changing too. You can kind of see that, how the orbit is changing. Make the Earth, or the sun really massive, and now the planet, oh, is it going to crash? Oh, wow, it's close. So I really increased the mass of the sun, so I changed the orbit of that planet, but now it's going to set down into a new orbit, a different orbit, a nice elliptical orbit. Okay. So you can play with this, it's kind of fun, play with the mass of the planet, mass of the star, see what kind of orbit you can come up with. Let's pause that and reset it, but let's go to this one with the Earth and the Moon and the Sun. Let's turn off the gravitational force. Let's turn off the path, and just watch. As we play this, you see the moon going around the Earth. By the law of gravity, the moon goes around the Earth. And it looks like the moon is making these nice little circular orbits around the Earth. And they're close to circular orbits, not quite. But at the same time, the Earth is going around the sun. So we're kind of looking at this from like the sun's perspective, the sun's reference frame. So now if I turn on the path of these objects, think about the path that the moon is making. It's not just simply going around the sun. It's going around in this weird shaped orbit around the sun because it's also going around the Earth. So if we turn that on, you can kind of see that reddish, whatever color that is, path is the path of the moon as it goes around the sun. And it has this weird path because it's doing both, going around the sun and going around the Earth as it travels. So that's kind of neat. And you can change the mass of the sun, you can change the mass of the Earth and see how that affects the moon. You can also look at the Earth and a satellite. So there's just the Earth without the sun and a satellite going around. So the law of gravity, Newton's law of gravity, governs not just planets going around stars, but anything going around anything else. A satellite going around the Earth, or a moon going around a planet, a moon of Jupiter going around Jupiter, and so on. So this is a fun little thing to play with. So this is the idea that I was talking about, where the star actually orbits, even though it looks like it might not. It actually orbits. The way we can kind of understand this is that if you had two objects that were the same mass, there's kind of a balancing point in between. If you imagine them being kind of connected by some wire or a rigid rod or something like that, you could balance that system at a point directly in between. Well, the stars don't really have rigid rods connecting them, but there's a force of gravity pulling one toward the other, and to keep them from colliding with each other, they have to have some velocity. Kind of, this guy is going to move this way, and this guy is going to move this way. As long as they're moving fast enough around in an orbit, they'll never actually collide. But if you have two stars that are identical in mass, they'll actually be executing exactly the same orbits, and they'll kind of be following one after the other, and they'll always be opposite each other. They're always opposite each other. So this would be the center of the orbit. This place, it's called the center of mass, that balancing point. Now, if one star is bigger than the other, that center of mass gets closer to the bigger object. And again, because if you think about balancing this, if you had like a rigid rod across here from the two stars, if you try to balance it, you'd have to kind of stick your finger or stick this pivot closer to the bigger object to balance it. And so if these two guys orbited each other, this one would orbit in a smaller orbit like this, while this one orbited in a bigger orbit around like this. And then they'd always be opposite each other, opposite on either sides of the center. Now, if you think about a small planet like the Earth and a big star like the Sun, the center of mass is actually really close to the center of the star. And so again, the star would be orbiting around a little tiny orbit around the center. So the star, it would look almost like, if the star was big enough, it would look almost like it's not moving at all. But if you look really carefully, you would see that the star is actually wobbling back and forth. It is actually making a very small orbit. And the period, the amount of time it takes to kind of make one wobble, is the same as the amount of time it takes for the planet to go around once. So while the planet is making a really big orbit, the star is also making an orbit, but it's much smaller. And so that motion is much more difficult to see, because it's a much smaller orbit. So objects orbit around, systems of objects orbit around their centers of mass. So Newton's law, again, is a law for anything. Anything can orbit anything. The law of gravity applies to any mass. And we can determine the total mass of a system, the total mass of, say, the planet and the star, or the two stars, or the star and a satellite, or a planet and a moon. We can determine the total mass of that system just by measuring the properties of the orbit, the period, and the distance, for example. So, for example, if you look at Earth's orbit, Earth goes around the Sun in an orbit of 1 year, and it has an average distance of what we call 1 astronomical unit. That information allows us to calculate the Earth's mass plus the Sun's mass, that combination. Most of the mass, though, is the Sun's mass, and so to a good approximation, we can kind of ignore the mass of the Earth because it's so small compared to the mass of the Sun. So again, measuring properties of the orbits allows you to get the total mass of the system. If you measure the orbital period and the distance of a satellite from the Earth, because the satellite's mass is so small, you're effectively then getting the Earth's mass. You can calculate the Earth's mass from measuring properties of a satellite's orbit. Or if you look at the moons of Jupiter, if you were to carefully measure the orbital properties of one of the moons of Jupiter, or measure its distance, its radius, how big is this orbit, and also how much time does it take for the moon to go around, you can use that to measure the mass of the moon plus Jupiter. But because the moon is such a tiny object compared to Jupiter, that total mass is essentially just the mass of Jupiter itself. And so you can get a very good approximation, a very good idea of the mass of Jupiter. So we can look at actual equations for this. So if you're interested, this is the equation that you would use. So this P is the period, the amount of time that it takes to go around once for, say, a satellite to go around the Earth, or whatever it might be. There's the number 4, and there's the number pi squared, and there's your big constant g that we talked about. A is the average distance from the planet to the center of the star, for example, or it's the average orbital radius. And so if I had, say, a satellite going around the Earth, this A would effectively be the radius of that orbit, the distance from the satellite to the center of the planet. The planet isn't moving much. We can pretty much ignore the motion of the planet because the satellite is so tiny, in a similar way that we can ignore the motion of the Sun because the Earth is so tiny compared to the Sun. So if you measure the average size of the orbit and the time it takes for the planet to go around, or whatever it is to go around, we can take these quantities, we can solve for the two masses, the masses added together. And so this just rearranges that equation. So we just have to take this 4 pi squared, multiply by the average distance cubed, divide by this big G, and then divide by the period squared. And this period would be measured in seconds. This distance A would be measured in meters, all standard units. So we can measure the total mass of the objects. So in summary then, we talked about the law of gravity and how it depends on the two masses, the product of the two masses, and any two masses will attract each other. And it's inversely proportional to the distance squared. So the bigger you make the distance between the objects, the weaker the force gets. And then Newton's laws can actually explain, and we didn't show all these explanations, but Newton's laws can actually explain Kepler's laws. Mathematically, you can show that if you have the law of gravity applied between a planet and a star, then you will have one of these three types of orbits: ellipses, parabolas, or hyperbolas. And all of Kepler's observations showed that the planets orbited in ellipses. And a circle is a special case of an ellipse. But the Earth's orbit is close to a circle. It's not a perfect circle. It is an ellipse. It's hard to find a perfect circular orbit. And then we can, by measuring carefully those orbits, we can measure the mass of the whole system, of the planet and the star, or the moon and the planet, or maybe two stars orbiting each other. We can determine the total mass of those objects. So that's all for now. The last thing we'll talk about from this chapter next time is thinking about tides, and how does the gravitational pull of the moon on the Earth and the sun on the Earth give rise to the tides that we know and love. So have a good evening.